Okay, so this section is a slightly odd section still in the course. It is to do with the fact that it is possible to approximate a binomial distribution using a normal distribution. On the screen currently, you can see that I've got a binomial distribution at the top and I've got a normal distribution at the bottom. The binomial distribution at the top has a p-value of 0.5. As a consequence, it is a symmetric distribution. And although I haven't actually lined up the kind of things at the bottom, they're quite small, I think you can see that the two shapes are very, very similar. However, let's remind ourselves that they are really different. This is discrete and this is continuous. Also, the heights of the bars in discrete represent probability and the area represents probability in a continuous. Nevertheless, it is possible to approximate a binomial distribution with a normal distribution. But why? Well, it is actually, in the past, it was very hard to calculate binomial distributions when there was a very, very large n. You were doing kind of lots and lots of summations. If you think about a binomial distribution, it's got a huge number of parts to it. So what people did was, in the cases where, and this is important, n is large, and p is close to 0.5, it is possible to approximate a binomial distribution with a normal distribution. So if x has a normal distribution, a binomial distribution np, it is approximately np as the mean and np 1 minus p as the variance. So just to be clear, mu is np and the variance and the standard deviation is the square root of npq or np 1 minus p, depending on whether you talk about q being 1 minus p, the probability of failure. The variance one is kind of slightly hard to really get your head perfectly around, but the mu does make intuitive sense. It does make intuitive sense. Think of like this is the average number of successes you would expect. So if I rolled the dice 60 times, you would expect 1 in every 6 to be a 2. So you'd expect to get 60 times 1 over 6, 10 2s. So it's kind of like, it kind of intuitively makes sense. This one, there is reasons for it, but we don't really need to know it. It's important for us to kind of see that at the moment. So if n is large, i.e. it looks like this. If n is really small, it stops working. We say n is large is kind of greater than 30. If p is close to 0.5, so if it was 0.45, that's all right. If it's 0.55, that's okay. In fact, the bigger the n, the more flexible we are with p. But if the question says use a suitable approximating distribution, you know that it's going to be kind of okay to do. Now, there is one other problem that we've come across. The next thing that we need to say is there is something called continuity correction. We came across that before when we said that the probability of x equaling less than or equal to and less than is different in discrete, but it's the same in continuous. So we've got to kind of solve that problem, and it's called continuity correction. So because we have a I've used this sheet is slightly I used this sheet before for Poisson. Poisson distribution is not something we need to know anymore. Because we know that in a binomial distribution x is less than 3, we know that that is different to x is less than or equal to 3. We have to think, what are we going to approximate it by when we switch from binomial over to normal? And it's kind of different. So this is how we do it. And I always draw a little picture. And what I do is just around the number that I'm interested in, I just kind of draw a little bar graph. And what we actually kind of do is we fatten up each of the kind of values, and we're going to go halfway in between depending on what the value is. So this is what we're going to do. Probability of x is less than 3. I'm going to look at this. I'm going to shade in the bits that are less than 3. So less than 3 is 2 and below. And hopefully you can see that what we've ended up with, I'm going to go red, is this would be a sensible point for us to take if we were to make it into a continuous. So at the moment it's discrete, 0, 1, 2, 3. But if we went continuous, it makes sense to go there. So when we do the normal approximation, we're going to say this becomes x is strictly less than 2.5 because it is halfway between 2 and 3. But we know that less than or equal to 3 is different. We get a different value. So what I do is, again, shade it all, but we're including 3 this time. And with a little bit of thought, we can see that this time it would make a lot more sense for us to do the probability of x is less than 3.5. So although we had 3 here and here, we've ended up with 2.5 and 3.5 when we've moved across to a continuous distribution. Do a couple more. Greater than 1 on binomial is going to be this stuff and above. So looking at now, I'm going up to here. So this time I'm going to say that that would continuity correct to greater than 1.5. Greater than or equal to 1. I'm going to include 1 and go above. So this is going to become the probability of x is greater than 0.5. Very similar to above. I would say people sometimes try to come up with a rule of adding or subtracting 0.5. Personally, I just like drawing a little diagram and I get it right every time. It can become quite complicated if you try to come up with a rule because it kind of gets a bit funny. I'm going to skip less than or equal to 4. We did one of these already, but I'm going to do these last two. Equals to 1. Now we know that when it was a continuous distribution, equal to 1 has a probability of 0, but in a discrete distribution it doesn't. So if I have equal to 1, I actually have to shade in the whole of 1. So this, on a normal distribution, we need to go between here and here. So this is between 0.5 is less than x is less than 1.5. So if it's discrete and it's equal to something, I can actually get an answer for my continuous, but it is going to be between two values. Greater than 1 and less than or equal to 3 is going to be these two bits. And so I get the probability of greater than 1.5 up to less than 3.5. It's very, very easy to forget to continuity correct when doing these questions. It's really, really easy. So you've got to be super, super careful to remember to do it. It's not that hard as long as you remember to do it. So what would a problem look like? We've kind of done all the theory, so let's actually look at a question. Again, I'm going to say this is very generous. Because the calculator can do it now, it's not going to be 7 marks. It's going to be more like 4, maybe something like that. So don't look at that and think this is going to be great, because it might not be quite. In a large college, 58% of students are female and 42% are male. A random sample of 100. So I've got, I'm going to find half are female. I'm going to say my P is going to be 0.58. My N is 100. P is approximately 0.5. And N is large, so a approximation is suitable. And I want to find but the normal the distribution we've got is a binomial distribution with N is 100 and 0.58. But I want to approximate, and I want to find P is X is more than half of the sample are female. More than half. That means I want greater than 50. Greater than 50. So now let's do our approximation. Suitable approximation is normal. It will say this language in a question. Suitable approximation. Suitable is normal. It's suitable because n is large, p is 0.5. So we're going to approximate this with x is normally distributed. I'm going to run out of space. And I'm going to work it down here. I'm going to say mu is equal to 100 times 0.58. And sigma is equal to the square root of np 100 times 0.58 times 1 minus p, which I've got is 0.42. And then that is going to be my approximation. So I have got, well, I can easily work out mu in my head because that's 58. That's expected, 58 out of 100 females. That's what you would expect. That makes sense. Square root of 100 times 0.58 times 0.42. That is going to be my sigma value. It's 4.94, but I'm going to store that as A because I'm going to use it in a second. 4.94. So 4.94, that was my sigma value, so it's 4.94 squared, and I can see that this is 0.58. So I am going to say that this probability in a normal distribution, sometimes people quite like to use a different letter there. I think I'm going to actually. It's kind of slightly neater, and I'm going to call that y. My normal distribution, so it's approximately, so actually I'm going to change that symbol to approximately. This is greater than, and now I need to continuity correct. So just do a little diagram on the side. I normally just do 3 bars just to kind of think about it. I'm going to put the one I'm interested in the middle, 50. 51 above, 49 below. Do my continuity correction. If this does not take too long, people often say, oh, it's too much writing, but it's not too much. Just draw a little diagram. I want greater than 50, so I am going to say here. So my cutoff point is 50.5, so I'm going to approximate it as greater than 50.5. So my normal distribution, like this, 50.5. So let's go to the calculator. So I know my standard deviation is that. I'm going to go into distribution. I'm going to go to normal CD because I want to find the probability. I'm not doing an inverse normal. My lower is 50.5. My upper, I just want greater than, so I'm going to put 99999. My sigma value, hopefully, I stored that as A. Did I just store that as A? It's 4.94. That'll do. 4.94. And my mu value is 58. 0.9355. 0.9355 equals 0.9355, which is an approximation of this answer. Now, the thing here, actually, I'm just going to double check that I can't get a more accurate answer. Did it actually store that as A? No, that's good. So let's just see if it gets slightly different. 0.9357 actually would be a slightly better guess. A little bit too much rounding there. They would be generous to allow that if you had clearly written down what you were rounding it to. Probably use 4 decimal places there, but I've got my kind of value here. Just to round this up, just to show you that it is a little bit silly us doing this at all, I could actually do this with a binomial because it isn't kind of ridiculous for us to kind of to just do this with binomial. So I'm going to show you, we want binomial cumulative distribution. That is going to give me 1 minus the answer. I want to do 50 or less with n is 100 and p is 0.58. I get this probability. And if I store that as b, 1 minus that, because I got less than or equal to 50, 1 minus the value I just got, I get that, which is pretty much what I got. Not quite, because it was an approximation, but this is the actual exact answer, whereas what I get was just an approximation, so it's a bit weird. Why are we doing it? But it is something we still can do. We can approximate a binomial distribution with a normal distribution. Okay, questions that you should try in the exercise at this point. So I am going to give you a couple of questions that you could try. So to do this, I recommend you go to exercise 3F and do questions 1, 2, 8 and 9. And that should cover that stuff well.